Mark.
Dear Heavenly Father, we're thankful for this day. We're thankful that we could be back at school to learn. Ask thee to bless us and help us to apply the things we've learned in comfort. Help us to understand the things we're learning here in class. In the name of Jesus Christ, amen.
Amen. All right. So when we left off on Friday, we had just started on the energy equation, right? So we finished up the momentum equation. We're starting on the energy equation. We gave an outline. We're going to follow a pretty similar outline to the energy equation that we did for momentum. We're going to start out and talk about how to get an equation of change for temperature. How do I get an equation of change for temperature? Similar to the question of how did I get an equation of change for velocity? The equation of change for velocity, we had a name for that. That was the Navier-Stokes equation. We won't be so lucky to have a name for the equation of change for temperature. There's no name for that one. You can make up your own. Maybe we'll call it the Knox equation or something like here that we had some dispute about this and heat transfer, maybe some anyway. So we can come up with some name for that if we want, but we're going to talk about that first, and then we're going to talk about how to solve that, okay? And just like we did before, we're going to talk about some simplifications and some dimensional analysis and how that allows us to think about simplifications of that equation. Then we'll do some simple examples, and then sort of punt on the complicated examples, which we're going to spend the second half of the class probably, a significant chunk of that time doing that, okay? So we started out talking about, all right, any questions real quick about what we're doing before I walk in? Okay, so outline, all right, that's where we're going. So we started out with the total energy equation just to remind us where we were, because I think we just started this with 10 minutes left on Friday. So perhaps you could be excused from checking out at that point. I don't know, it was still the morning, so I think you still should have been with me, but you never know, okay? So we did a energy balance on a differential sized cube, right? And we've been doing lots of these differential balances, so hopefully this isn't like crazy nuts by this point. And then I think the energy balance is pretty easy because it's just a vector as opposed to say the stress tensor, which we had to do before, which is a little more complicated to wrap your mind around. But so we did an energy balance on a cube, and we found an equation that looks really similar. And I think by now we should be expecting to find a time derivative term of the total quantity, right? And then a divergence, right? A minus divergence of the flux on the right-hand side, okay? It turns out they're all that way, right? Like that's what happens when we do these balances. So we get an equation that's exactly of this form, right? So previously we had the divergence of the stress tensor, and we had the total momentum here. Now we have the total energy here, and we get a divergence of the energy flux. Okay, and so that's where we got to. And just to remind you, this is GH, okay, so that's rho GH right there, but BSL likes to use a little P hat, okay, capital P hat there. All right, and so we got to this point, and so this we know, that total energy flux we know from our previous work with these energy fluxes, right? And there's three terms in here. So this one, if you recall, is the convection term. Okay, so this is the energy, this one I guess includes the field right there. It includes the energy that we're convecting in and out of the box, right? So if that was the only term here, that would be energy flows in, energy flows out, all right? And then this one is a work term. Okay, it kind of looks like P delta V, right? If you think back to thermo, or you're probably thinking of thermo now. I heard someone say doing thermo homework over the weekend. Hurts my feelings a little bit, but that's fine. I understand. That's probably due today, right? Yeah, there you go. Okay, so that's a work term, and then there's the heat term. Okay, so there should be some overlap between thermo and today. I don't know. What are you guys doing in thermo right now? Just out of curiosity.
We're solving equations of state for things other than like Z and pressure and stuff like that. So like gas coefficients and equilibrium temperature.
Are you doing single component phase behavior? Okay. Okay, so anyway, so these are the different parts of the energy equation, all right? Or the energy flux rather. So this we're gonna have to plug into there to get our final energy equation. So let's do that really quickly. This will give us our final sort of box solution. So if I just take that and plug it into here, I'm gonna have the divergence of this, the divergence of this, and the divergence of that. Okay, expanding that out, and that's all that I'm gonna get at the end. So we'll see if I run out of space or not. I'll just do it over here. I know I'm gonna run out of space. EDT of 1/2 rho v squared plus rho u hat plus rho e hat equal to minus, hold on, where did I lose my del dot. Okay, now this guy has to go in there. 1/2 rho v squared plus rho u hat plus rho phi hat v, close the square bracket, okay? And then I have another minus del dot, and then this guy goes in there, pi dot v minus del dot q. I'll put a box around that guy. Okay, and I'm going to call this the total energy equation or the total energy balance. Okay, which I'm going to abbreviate by T. Okay, so let me make a couple of comments about this. So this is really just an expression of the first law of thermodynamics. Okay, this is just U is equal to Q plus W. All right, it's the same thing, okay, but it's for an open system. So we talked about this when we talked about the shell balances, when we talked about open systems. So we've seen open systems before, okay, but now it's also an open system where stuff can vary in 3 dimensions. Right, so it's a generalization of that equation. So when you see this, I want you to think in your mind, U equals Q plus W. All right, just like when we talked about the Navier-Stokes equation, and we see F equals M and N. All right, the same principles here, just more math, more varying in space. Okay, but it's the same idea. Okay, and then the other thing is we should know the meanings of these terms. So we just talked about them, right? But we should know what each of these terms means. Sort of when we think about our blocks, right? So we should, when we stare at this, we should think, okay, U equals Q plus W, and then we're saying, okay, this is the energy terms that's in the box, and then this is what's going in and out, and then work and heat flow. Okay, so hopefully this shouldn't be too mysterious, right? By this stage, hopefully we're starting to get used to upside down triangles everywhere and not feeling too intimidated, right? But one of the things I hope we get out of this is that you should see math and you should see what it's physically saying, right? Like that's, what is this really telling us that we're doing here, right? And I think sometimes as an undergraduate, what happens is you look at this stuff and you just kind of see symbols and it's like, oh, this is something really complicated. Okay, and the reason we have this short kind of Gibbs notation, the reason we try and do that, so that we can have that perspective on a set of equations, right? And that's what, when you're reading a paper, right, and you look at, there's some equation, right, and you see, oh, like that pops up. If you have to sit out and write out all this stuff, like that's not the point. The point of writing this down is for you to go, oh, I see that. That's the energy equation. I see what the terms are doing here. That's the kind of high level thinking that hopefully we're developing by. All right. One more thing just to say, we remember that this pi term has both the viscous stresses and the pressure in it. So we can divide this, if I said del dot pi dot v, I can write that out as del dot as p delta plus tau on v. Okay, and that gives me del dot PV plus del dot tau dot. Okay, so. Okay, so just to recall that, that'll be useful for us to think about in a minute. Okay, so now we have the total energy equation. That's nice. We see these nice analogies with thermo. It makes us maybe feel warm and fuzzy. We know where it comes from, okay? But kind of useless to solve something, right? I mean, there's so much going on here. There's, kinetic energy, internal energy, potential energy, there's convection, there's heat, there's work. There's just so many things in this equation. If I give you that, you don't know where to start to solve, right, the problem. If I say find a temperature distribution, you start with that guy, you're like, all right, great. That's really complicated. There's tons of unknowns. How do I isolate temperature out of that? What are we going to do? Okay, so today we're trying to get to the equation of change for temperature, just like a couple of days ago we tried to get to the Navier-Stokes equation. Okay, so that's what we're trying to get to. So one of the things we'd like to be able to do then is find another equation to maybe simplify this guy down. Okay, and we saw an equation where we had velocities and other things in it. We had the momentum equation before. So let's write down the momentum equation, the total momentum equation, Cauchy momentum equation. You remember it was d dt rho v is equal to minus del dot rho v minus grad p minus del dot tau plus rho g. Okay, so this is the Cauchy momentum equation. You remember that was the thing before we plugged in Newton's law of viscosity, before we said it was constant density and simplified it to the Navier-Stokes equation. And this has a rho v in it, and that has a rho v squared. And so it occurred to people, they thought, well, let's take the dot product of this equation with v, and we should get something that looks like the kinetic energy. And then maybe we can take this and subtract that and get rid of the kinetic energy term. Okay, like that seems like that should be possible. This is a separate equation. We know it from momentum balance. So maybe we can use that to say something about the kinetic energy. Okay, so let's do that. Let's take the, v dot of the Cauchy momentum. Right? Now let's do that math and see what happens. Okay, so the problem with this is that you get lots of algebra. So I'm not going to do it in every gory detail, okay, but I think you should. I think you should sit down and work this out. Okay, so I'm going to sketch some of the steps, and I think you should take some time and fill it in between. Okay, so let's just write down what it looks like. If I do d dt of rho v, ooh, I don't like that v. I'm going to fix it. Okay, and I'm going to do the dot on the right side. It shouldn't matter if I do it on the right or the left side because it's vector equation, so vector dot should be the same. If I'm not mistaken. Minus del dot rho v v dot v minus grad p dot v, and then minus del dot tau dot v plus rho v dot v. Okay, so the trick to this is that if I want to get the kinetic energy here, I have a problem in that the velocity is on the outside of the derivative. Okay, and the same thing over here. If I want to make a v dot of v, and if I want to do anything where I mess with those velocities, they're outside of the derivatives, right? These derivatives have sort of an implied parentheses around them, right? So what do I do? How do I get something inside a derivative? Well, I don't really know how to get something inside a derivative, but I know how to get something out of a derivative. So if I had a term that was like this, d dt of rho v dot v, I could use the product rule to get that out, right? So then I could say that that's the same thing as d dt of rho v dot v plus rho v dv dot. Something like that, right? I could do a product rule and then play that game. So now if I look at that and I think, okay, well, what I can do is solve for this guy right here, okay? And it turns out if you look at this, maybe the right way to think about this is I don't have to pull the row out. So I can actually write that as v dot d dt of rho v. Isn't that right? Did I do that? Let me think about that real quick. Make sure I don't screw that up. I can say that, but should I then have another row? Now I got stuck. Row B. Right? And then if I can, that's my confusion. All right, I don't know. I have to think about that for a second. I'm stuck. Can anyone help me? Do I have to leave the row out, or can I put it in? I confused myself.
If it's not dependent on time, you should be able to put it in or out if it's just a constant.
Well, if it's a constant, but if it's not a constant, I can't just play the game, right? I have to try to remember here. All right, we're going to move on for a second. I don't want to hold this up. I'll think about that. I'll make a note in my notes to make sure that I think about that. See, and I'll correct it next time. Let me just ask that question here. Little question mark. dt of rho v I v I. Question mark. Okay, sorry about that. Okay, so if I can write it in this form, notice that this is just 2 times this guy, right? V dot d dt of rho v. Okay, and this one over here, v dot v, that's v squared, right? So I can move the 2 over here, and I can say 1/2 d dt of rho v squared is equal to v dot d dt of rho v. Okay, well that's what I just wrote right there. Okay, so I can substitute 1/2 d dt of rho v squared in for the thing I already have. That makes sense? That makes sense, Roya? Thinking about it. So I can take that piece, put it right there. So now I have 1/2 d dt of rho v squared is equal to all that stuff on the right, minus del dot rho v dot v minus grad p dot v minus del dot tau dot v minus rho g dot v. Okay, so that's looking promising, right? I have something for rho v squared, okay, here, and I had something for rho v squared here, so that's looking pretty good, okay? But I still want to go through and simplify these other terms. So the same trick that I used where I said, I kind of want to do an inverse product rule, okay? I need to play that game with all of these other terms. So this one, and this one, okay? I have derivatives, and I want to do the thing where I take the velocity and move it inside somehow, right? So instead I take the product rule where it's already inside, and then I expand that out, and then I make the substitution back in, okay? They all don't collapse just to a term with the 2 tons like this. Most of them, they come out, they have 2 terms, all right? So I'll write up what we get when we do that process. So that's just a bunch of algebra, calculus and algebra, I guess. This is why these markers are the worst. Leave a little bit behind. All right. We're going to leave that up there for a second. Okay, so what do we get to? We get to this guy. We 1/2 rho v squared. Okay, that I know I can bring the 1/2 in because it's a constant. Okay, then I get minus del dot 1/2 rho v squared v. Okay, that one comes from the first term over there that I underlined, plus p del dot v minus del dot pv plus tau double dot grad v minus del dot tau dot v minus p g dot v. Okay, so do you see the first term here became this term with the 1/2 rho v squared? Okay, and then the other terms, I had 2 terms left over. So I made that substitution doing the product rule, but they just became 2 terms. Nothing got really simple. Okay, now we have this term hanging out, this rho g dot v. I need to do something with that guy. Okay, and you can rewrite that one as rho v dot grad phi hat. Okay, remember that phi hat was equal to gh. And then grad phi hat is equal to minus g. Is that that's supposed to be a rho, not rho g dot v. Okay, so I just get the minus g there from that guy. So that now looks like one of these derivatives with the grad. I want to write it in terms of something like grad v phi hat. Okay, how do I go about doing something like that? Well, it turns out that looks a lot like, actually I want to put the rho in there too. That rho v, that looks a lot like the continuity equation, and I can end up using the continuity equation to substitute in, and I get a time derivative of a rho phi hat, and then another term that looks like this v dot grad phi hat 1. Okay, so when I do that substitution, I get d dt of 1/2 rho v squared plus rho phi hat is equal to minus del dot 1/2 rho v rho v squared plus rho phi hat v plus, and then these four terms that I have from before. E del dot V minus del dot PV plus tau double dot grad V minus del dot tau dot V. Okay? So again, I skipped a bunch of algebra there to do the continuity equation. I'm sure that was a little confusing. I'm not sure I explained it very well. Okay? But I make this substitution for phi, and then I play the same product rule game, and I need to use the continuity equation. That's how I get this piece on the left-hand side. Okay? And then the other part from the product rule gives me this part that has the velocity here. And now this is starting to look a lot like my total energy balance, right? There's some different terms, but there's some terms that are pretty similar. Okay? So now this here then is the end equation for this part. And this is called the mechanical energy balance. So this is the mechanical energy balance. Okay, I'll write that as MEB. Okay, sorry. Total energy balance TV is mechanical energy balance. Okay, so we got another equation that has energies. Okay, so why is it the mechanical energy balance? Well, these two quantities, the kinetic energy, right, and the potential energy, those are the mechanical energy terms, right? If you think back about mechanics when you took freshman, physics, that's what we were talking about, the mechanics, right? So, that makes sense. If you have F equals MA, you can also multiply it by, something and get energies, right? You did lots of energy problems in freshman mechanics class, right? And so you saw trade-offs between kinetic energy and potential energy, okay? And now we've written that for a fluid, okay, in which we have gradients and all this stuff. So let's think about what these terms mean to make sure that we know what's going on here. Okay, so the first thing to say is like, look, this looks like a balance equation, just like our other balance equation. We've got the change in the box of mechanical energy, right? And then we have the convection of mechanical energy in and out of the box. And then we have these four other terms, okay? And we know from a balance that if we have, the thing and then in minus out, the other terms have to be generation terms, right? Sources or sinks. That makes sense. We have mechanical energy. It's not conserved, so there's sources and sinks going on in mechanical energy, right? So, okay, so what do these terms mean? So this one right here, this is expansion or contraction, okay? So, okay, and if you look at it, this is P times that expansion or contraction. That looks like a P delta V term, right? So I can either expand or contract my fluid. Some other ways to help remember that is del dot V is 0 in an incompressible fluid. So I'm compressing, right, or expanding my fluid, okay? This term is a reversible term. We'll talk about that a little bit more in a second. And I'm just going to write that up for now, okay? This one is the total PV work. Okay, we saw terms like that in our total energy equation. Okay, that's going to prove useful. Okay, this is a term called viscous dissipation. Okay, this is my shear stresses times by volume changes. Okay, so it's sort of the analog of this guy. Look at them, they came kind of from the same piece in a way, right? Just one had the pressure and one had the shear. But these ones are irreversible. Okay, so when I do shear and I have, changes in velocity, I'm not going to be able to get that back. So this is like a heat generation term we'll see. It's how I'm turning mechanical energy into heat. This one is irreversible. Okay, and then that one is sort of analogous to this guy. It's the total work by shear stresses. Okay, or viscous forces. All right, questions about the mechanical energy balance, how I got here, what it means, are we comfortable with it, we're happy. Double dots finally make their appearance, right? We learned it for a reason. Good, Andrew, happy? I can't see your smiling face underneath the mask. I just see eyes. They could be bored, they could be excited. I don't know. Okay, so now C total, or excuse me, total energy equation. Okay, so now for the internal energy equation, what are we going to do, Brian? How are we going to get that? I've already said it. I already gave it away earlier. Just checking to see if they're awake. I'm not awake. Who can help Brian? What are we going to do? What do you think, Mark?
Subtracting the total energy, subtracting the mechanical energy from the total energy.
Exactly. I'm going to subtract the two, right? So I don't want to write up, one reason I didn't erase is because I didn't want to have to rewrite that guy and then write that and put minus signs, right? And do that out. But let's just stare at that for a second. I'm going to subtract the mechanical from the total. So what terms are the same? Well, that term appears, right? That term appears, so that's going to cancel. That term appears and that term appears, so that's going to cancel, okay? And then I said, look, I expand these guys out, and I get this one and that one. Well, those two are up there, right? So that one appears and that one appears. So this guy is going to cancel. All right. So the internal energy equation is just the pieces that are left over. So d dt of rho u hat is equal to minus del dot rho u hat v. Okay. And then now I'm going to have minus p del dot v, right? And I should have a minus that term, minus tau double dot grad v. And then I should have that guy come survive, minus del dot q. Did I miss anything? I don't think so. Okay, so now I can do one more step of simplification to make our life a little easier. I can write a material derivative after I do a couple steps of simplifying this. Remember, the material derivative is rho d dt plus rho v dot grad something. That goes in there. That doesn't quite look like this. There's still a rho in here, okay? And I've got the v inside. But if I do out a product rule of that, I get a continuity equation that comes out. I get like a u times a continuity equation. And so that thing falls out and it ends up being 0. So I get like the two sides of the continuity equation that cancel. And I can rewrite this guy as rho u hat dt is equal to minus p del dot v minus tau double dot grad v minus del dot q. Oops. Okay, and now this is the internal energy balance. Okay? So quick comment. So the fact that these terms survive help us understand the meaning of what they were here. That's kind of how we know. Okay? They are terms that are mechanical energy that are converting into internal energy, right? So they're interconversions between the mechanical energy and the internal energy. So, I had these total energy terms, right, that ended up canceling there. But these things, I could take expansion or contraction here and take something that had kinetic energy or potential energy and then turn that into something that changes heat, okay? And then this one, the double dot, that ends up giving me squares all over the place, okay? And because there are all these squares, this one always has one sign. And the same thing happens over here, okay, the squares. And so that ends up making it irreversible, okay? Because I can't do anything to make it, I can't make it go from this way back to this way. But the del dot V doesn't have that problem because it doesn't have squares in it, okay? Because if you think about this tau has grad V's in it as well, right? So that grad V's times grad V's give me grad V squared. So that's how we know this one's irreversible, okay, but this one's reversible, okay? So I'm not gonna write out all the squares, okay? But I think you get the idea, all right?
True.
Yes.
We have made no assumptions to this point, right? This is still an exact equation.
Yeah, we made no assumptions, right? We haven't assumed Fourier's law, we haven't assumed anything, okay? So this is sort of like our, where we were at when we got to the Cauchy momentum balance, where we said, now we have to start adding stuff, okay? So this is the kind of extra stuff that comes in the energy equation. Is you get this total energy equation when you do the balance, okay? But then you have to do all this stuff now to get just an equation for the internal energy, okay? Because we actually don't care about the kinetic energy or the potential energy. When we're thinking about temperature, we're only caring about how the internal energy is changing. Okay, kind of makes sense in retrospect, and you're like, well, we had to do all that math to do something that makes sense, but you kind of still need to see where that comes from. Okay, so that's all of C. Other questions? That was a great question. I'm erasing here. Online, we still there? Zach and Dan? They're gone. They're eating a bowl of cereal or something. Making us all feel like suckers for putting pants on. This different brand of markers is the worst. Get a workout and then I start sweating up here just from erasing. Oh, out of shape. Professor that I am.
How's your knee?
It's feeling a little better. It's still a little glitchy. Didn't feel like I could go to basketball this morning. Give it another week, I'm hoping. Either that or I have to go to the doctor and have him scan it. Okay, so now we're on T. Equation of change for. Okay, so now we're trying to get our equivalent of the Navier-Stokes equation, but for temperature. Okay, so remember what I said before, I've said like a number of times now. In order to get an equation of change, we need two things. We need a balance and we need constitutive law, right? So in this case, we've got Q, so we need the constitutive law for Q, which was Fourier's law. So we need constitutive law. Okay, so Q is equal to minus K rad T. Fourier's law. Okay, so we also have V's in there, there are the tau in there, excuse me, okay? So we need to assume something about that one as well. So if we have the viscous dissipation term, we need to know tau is equal to minus mu grad V plus grad V transpose minus 2/3 mu plus 2/3 mu minus kappa. That's what it is. Del dot V delta. Okay, so the constitutive law for Fourier's law, that's going to give us the Q. If we want the tau in there, we need to use Newton's law of viscosity. So Newton's law of viscosity. Okay, we're going to use both of those guys. And taking this and plugging that into here, okay, is going to take care of the right-hand side of this equation, okay? And again, this is like 3 pages of algebra. Well, no, this one's not too bad. So it's just a little bit. Okay, that ends up giving us this, though. I'm going to save us a little time, hopefully. Skipping algebra. We get out rho u hat t minus p del dot v. And then VSL punts, because these are obnoxious. We write the following. Plus k grad squared t. Okay, so the easy one to see is this k grad t, right? That goes in here, delta. If k is a constant, so I assume k is constant here. Okay. If I assume k is constant, I get k grad squared t. Then there are these other terms, and I wrote this PV and psi v, or psi k, isn't it? What is it in? I have an NV all over the place. Maybe that's what it is in the book. These are the del dot terms that come from the tau. Okay, they're nasty. I have them somewhere. Where did I write them down? And rewrite them till the end. I'll write them up so we have them. So PV is equal to grad V double dot grad V plus grad V double dot grad V transpose minus 2/3 del dot V. Okay, so that's the thing that where the viscosity, basically grad V squared, you can think of it like that, okay? And then I subtract out the trace, so it has no trace. And then psi V is equal to del dot V squared. Okay? Right? So that's the right-hand side. On the left-hand side, we need to get rid of the U somehow, right? We need to get it in terms of temperature. So we're going to use the heat capacity to do that thing. And, or the left-hand side rather. So what about the left-hand side? Okay. What do we do about that guy? So there's kind of 2 ways to do it. You can either go through the U C sub V route, but the more common way is to do a Legendre transform. Maybe you've learned about that, Darla. Did you guys talk about Legendre transforms? Oh my goodness, bummer. Okay, so but it's not that complicated. H is equal to U plus V. Okay, that's a Legendre transform. It is to tell you. Okay. I should tell you that sometime in demo. Okay, or U plus P over rho. So in fluid mechanics and in transport, we don't like specific volumes. We call those inverse densities, right? Density is a lot better, so we like density instead. Okay, so if we use the enthalpy instead of the internal energy, we'll get C sub P's. Okay, and there's a little derivation. The book actually does it for you. Okay, and what you get out is following rho du hat dt is equal to rho dh dt minus dp dt, P is the pressure, plus P over rho minus rho del dot V. Okay? And that cancels expression. So there should be a minus, I'll just rewrite that, minus P del dot V. Okay, so now I can plug that in to the left-hand side over here. And now I'm going to get a rho dH dt, okay? And I can write that a little bit differently in a few seconds, but maybe I'll just write that up over here. So I get rho dH hat dt is equal to, I'll put the minus P over here, minus dP dt is equal to mu phi V plus K psi V plus K grad squared T. Okay, so the del dot V, P del dot V term cancels. Okay, and then there's a few more algebra steps. Okay, you can look in your book and work out. Okay, involves things like, if I write down dH hat is dH dt at constant P dt plus dH P at constant T dP. Okay, you can pull out the C sub P term, and there's another term here that has a dP dependence. Okay, and when you do all that out, you get that dH hat is equal to C sub P dt plus 1 over rho times 1 plus d natural log rho d natural log T at constant pressure dP. Okay, that comes out. So you can sub all of that back into the internal energy equation, and you get the following. Rho C sub P dt dt is equal to K grad squared T plus mu phi V plus kappa psi V minus derivative of the natural log rho, derivative natural log of T dP dt. Okay. And that is the equation of change for temperature. Okay, we'll call equation of change for temperature. Okay, so now that's our equivalent of the Navier-Stokes. So think about, we've got this, change in temperature on the left side, diffusion here, right? Then we have these terms that come from viscous forces, right? I either have the traditional viscosity, shear viscosity, or the dilatational viscosity that comes from expansions and contractions, okay? And then this term here, we'll review this again the next time, okay? This term here, I'm just telling you, so you don't have to go away doing so much with the cliffhanger, right? This term right here has to do with changes in compressibility, right? So this is like, I put the equation of state in here, and this is when I want to look at something like compressible flow. How does that change the temperature? So the density changes, that's going to affect the temperature over here. And so that's where my thermodynamic equation of state comes in to the temperature changes as well. Okay? So yes, and
You said diffusion. Did you mean conduction for that?
conduction, diffusion, Same thing. Yep.
And then could you repeat what mu and kappa, what those two?
Yeah, so these are both viscous heat generation terms.
Okay, so
Okay,
this is-
mu is our traditional shear viscosity. Okay, kappa, if you remember, that comes in right here. That's our dilatational or our volume viscosity. So when I have an expansion or contraction, okay, if there's a viscosity there, and so the losses that come from that expansion and contraction have kappa. Okay, so I get heat moving around by diffusion. These are generation terms. That's if I've got velocities, that's giving me heat. Okay, and then this one is exchanging. You know, it's exchanging heat when I've got, you know, density changes or pressure changes, etc. Okay, we'll talk more about that and how to solve that next. Okay. Oh God.